Hello, welcome to Q Chem webinar number 59. My name is Kuan Yu Liu, a research scientist here at Q Chem Pleasanton. It's my pleasure today to introduce our speaker, Dr. David Casanova. He'll be talking to us about restricted active space CI families of methods and Q Chem. David has been a ICABOSC research associate at the Nostia International Center since 2018. His research focuses on the development and implementation of electronic structure for excited states and strongly correlated systems. He also uses these methods to study optoelectronic magnetic properties of molecular materials and underlying photophysical processes. And without further ado, I'm gonna turn this over to David.
Okay, thank you very much. And as he said, so I'm gonna talk about restricted active space CI methods as they are implemented in Q Chem. But first of all, let me tell you a little bit about our group. So we work in the Basque Country. This is between France and Spain, and we are in a marvelous city. Donostia is in Basque, or San Sebastián in Spanish. And our research institute is the Donostia International Physics Center, which is within the limits of the university campus and not far from the sea, as you can see. So we are very fortunate. And I'm very lucky to work with a group of very talented and motivated PhD students and postdocs, and our research is focused on the study of electronic structure of molecules. We do development and implementation of methods to compute and characterize electronic states, and most of these methodologies are currently implemented in Q Chem. And lately, we have been also working on different methods for studying excited state dynamics or exciton transport. And we apply these and also other methodologies to the study of a variety of problems in chemistry, like strongly correlated molecules or different types of molecular aggregates. And we've been studying a large variety of photophysical processes. So this is basically the general picture of what we do in our group, and this would be the outline of the webinar. So first, I will motivate the use of a spin flip operator in order to compute electronic states, and I will discuss the basics of the spin flip or RASCI wave functions. This is the use of a spin flip operator with an active space. I will let you know about what I think is the main limitation of these methods is the effective lack of dynamic correlation. I will present a couple of attempts trying to overcome this limitation, both of them implemented in Q Chem, and then I will show you some examples or some tools that can be used to characterize electronic states computed with a RAS spin flip and also electronic transitions. So in quantum chemistry, we have to deal with this very complicated time-independent Schrödinger equation, where we have plenty of variables. And although we do have an exact solution, the so-called full CI wave function, the computational cost of full CI grows, at least in a classical computer, factorially with the size of the system, and that forces us to do approximations. And in quantum chemistry, we do basically two types of approximation. The first one is how well, or it's related of how well we describe single electrons, and we do that by choosing an atomic basis set. And then the second type of approximation is related with how well we describe electron-electron interactions. It's what we call the electron correlation problem. And we have plenty of different of those approximations implemented in Q Chem. And today I will talk about one of them. If we, as a chemist, I believe that most of us, when we think about the electronic structure of a molecule, what we have in mind is a set of molecular orbitals that we can order by their energy, where they have a spin alpha and a spin beta electrons. And then on top of that, at higher energies, we have a set of available energy levels, virtual orbitals. And this picture actually works very well for many molecular systems. And let's take the simple H2 molecule, where we have 2 electrons in the sigma bonding orbital and none in the sigma antibonding. And this is basically the description of the ground state of this molecule at the equilibrium distance between the 2 atoms. But as soon as we stretch this molecule, as soon as we separate the 2 nuclei, the 2 orbitals become closer and closer and in energy, and this picture breaks down. So meaning that the Hartree-Fock energy, which is basically corresponds to this configuration, departs and produces a much larger energy with respect to the full CI, the exact solution, right? And what people typically say is that, well, here, because we have 2 orbitals close in energy, one configuration is not enough, and we need a multi-configurational wave function to describe this situation. And this is true, but I must add, this is true for the ground state singlet, but this is not the case for the high spin triplet. In the triplet, we put 1 electron in each one of these orbitals, and it doesn't matter the separation between the 2 atoms. This triplet state is always well defined with just 1 oscillator determinant all along the dissociation. So spin flip methods take this fact as basically the starting point in order to build wave functions. And the idea is to instead of starting for the ground state Hartree-Fock-like configuration, we start from a higher spin state, typically a triplet, like in the previous case in H2, because even if the frontier orbitals are degenerate or near degenerate, this configuration will be well defined with just 1 configuration. And then we might apply an excitation operator that we call a spin flip operator, that takes alpha spin electrons and promotes them into beta empty orbitals. And by doing that, we get depending on the hierarchy of this excitation operator, we get a target state. Now, in this case, with the same number of alpha and beta electrons, so ms equals 0, where we have taken where we have used the well-defined reference, and we have plenty of these different methods that use a spin flip operator. And in Q Chem, we can, for instance, apply a spin flip to equation of motion coupled cluster, or ADC, or CI, or even linear response time-dependent DFT. And in the literature, you can find many different examples where spin flip methods are very useful, and in particular to study the ground state of diradicals, triradicals, or to produce a smooth bond breaking profiles, like in this case in the HF molecule, where we can see that in all these different methods we obtain a nice a nice dissociation curve, and adding more and more correlation, we get closer and closer to the exact solution. But not only for the ground state we can use the spin flip methods, also for the excited states, like here in this example in methylene, where the ground state of this molecule is a triplet state, and we have three low-lying states, which are different type of singlet states that we can recover rather easily with the spin flip method like QM spin flip couplet cluster singles and doubles, but we cannot do the same without the use of a spin flip excitation operator. But not everything is nice with these methods, and one of the limitations of problems that you might find when you use these methods and you compute several states is spin contamination. You can get different amounts of spin contamination depending on the situation. And let's take here, for instance, the simplest spin flip method, which is the CI singles. And let's start from a triplet Slater determinant as a reference. And if we apply the CIS spin flip operator, we will obtain configurations like this. But we will realize is that if we include all possible spin flip singles, we obtain configurations that are spin incomplete, meaning that we obtain a configuration where we have a spin up, spin down configuration, but we don't have its complement. And because this complement corresponds to a double excitation with respect to our starting point, our triplet reference. Moreover, we can see that if we include single excitations with respect to the triplet, we are missing some configurations that might be important to describe low-lying states because they look like a single excitation with respect to the Hartree-Fock like singlet, and if we include this subset of double spin flip excitations, we can define a new method which is called the spin flip extended CIS, which is all possible single excitations with a single spin flip and a subset of double excitations. And now this method is spin complete and also includes some additional contributions that might be important. Okay, but this is okay for a spin flip CIS, but this is a solution for this case, but it's not really a general solution for all the cases, right? So, and because of that, we decided to develop this method that we call restricted active space spin flip. And the goals or the idea was to take advantage of the good properties of a spin flip methods and the use of a spin flip operator, but make it more general and have operators that can flip any number of the spin of electrons. And we want a method that does not suffer from spin contamination. And we would like to also compute rather large systems, and because of that, we will be worried about the computational cost. So, like in let's say a standard spin flip method, in RAS spin flip, we start from a higher spin configuration that can be a triplet or can be any higher spin state, like in this case, quintet. And then before defining our operator, we split the orbital space in three subsets: RAS1, RAS2, and RAS3, where in RAS2, typically we have the set of singly occupied orbitals, although we are not forced to, but typically it's the one that we use. And then we apply our spin flip operator. And what we do is instead of using a singles or doubles excitation, what we do is we have all possible excitations within this RAS2 space. So meaning that in a sense, we have a full CI within this reduced orbital space. On top of that, we might add additional excitations that go beyond this RAS2, and we have what we call particle contributions, where we promote electrons from RAS2 to RAS3, or Hall excitations that move electrons from RAS1 to RAS2, and so on. And this scheme, first of all, is a generalization of the previous spin flip methods, because it allows you to deal with any number of strongly correlated electrons. And we have a clear scheme to treat different type of systems. What I mean is, like, we can use a single spin flip to study diradicals and triradicals, or break single bonds like before. But we can use a double spin flip to study tetraradicals, pentaradicals, or to break two bonds simultaneously, or in general any number of correlated electrons or polyradicals, right? And another nice property is that our wave function is by definition, or will be by definition, spin complete. So there will be no spin contamination. And the reason of that is how we have expanded the excitation operator. Instead of expanding the excitations in terms of singly, doubly, and so on, the number of excited electrons, we do that with respect to the excitations with respect to the RAS2 space. So all possible excitations within RAS2, Hall excitations, particles, and so on. Meaning that any truncations that we can do here will be will have all the elements to obtain wave functions which are pure singlets, pure triplets, or doublets, or so on. And typically the truncation that, for different reasons, the truncation that we use and is by default in Q Chem is the one that includes up to Hall and particle configurations. So this type of methods were emerged from the spin flip methods, but actually they can be more general, meaning that we are not forced to use only a spin flip operator. We can use other type of excitation operators, like like operators that conserve a spin, but also operators that do not conserve the number of electrons, either add or remove electrons to the system. And at the end of the day, we will have a wave function, which is a CI wave function. So a linear combination of Slater determinants. And in Q Chem, each of these configurations appear like a occupational string. So a set of orbitals with a spin alpha orbitals with 1 or 0 electrons, and the dimension of this space of all possible excitations that we call active within the RAS2 space obviously has the dimension of a full CI within this RAS2 set of orbitals. But then also we have Hall configurations that where we have to add an index of the index of the Hall, and the size of these contributions grow linearly with the number of occupied orbitals, meaning the size of our molecule. And then particle configurations. Here we need to add another index, which is where the orbital where the electron in RAS3 where the electron goes, and the size of this subspace is linear now with the number of virtuals, or in other words, with the size of the basis set. So then, like other CI methods, we have to diagonalize our CI Hamiltonian, and of course, because of the size of these vectors, we do that iteratively, and the interaction terms contain 1 and 2 electron integrals, and in Q Chem, RAS spin flip and RASCI in general is implemented basically following an integral driven algorithm, which is common for CAS methods or for full CI. And what I mean by that is that the program runs over all different 1 and 2 electron integrals, and for each integral, it identifies what configurations interact through this integral. But we also mix some configuration-driven parts of the code, and this is mainly because of these Hall and particle contributions, where what the program does is instead of running through the integrals, we run through the configurations, and for each configuration we identify the interaction terms and the configurations that interact with each one of these. This is typically done in linear response to DFT or CIS methods. Okay, so if you go to the Q Chem manual, you will see that actually there are in Q Chem 2 different versions of this method. So the method is the same, but there are two versions, and the reason of that, because of that, is because we have a version that works with exact integrals, is the one that we develop, and there is a second version that instead of using these integrals makes use of the resolution of the identity. So in order to work with one or the other, we as it is well explained in the manual, you have to use either correlation RASCI or correlation RASCI2. So you can find all the details there. So okay, so this is the method that we have been developing for the last years, and now let me tell you a little bit about the lack of dynamic correlation in this type of wave function. And the main reason for that is because of the truncation that we do to our excitation operator. So as I said, we include by default all excitation within RAS2 plus Hall plus particle excitations, but we don't have Hall particle, 2 holes, and so on. And because of that, we are missing correlation, and we believe that we can label this type of correlation as dynamic, mainly dynamic correlation. And it has an important impact in the energies that you obtain with these methods. And let me show you here just an example. So here is HF molecule, and here will be we have the energy of full CI and correlated methods for closed shell system, and here is Hartree-Fock. If we use RASCI with a small active RAS2 space, we obtain an energy which is much closer than Hartree-Fock than this method. So this is clearly an indication that dynamic correlation is not here, right? where like in contradiction of what we have, for instance, with MP2 or CCSD. And of course, this lack of dynamic correlation has also an impact in the quality of the relative energies that we compute between different excited states, and it is important to be aware of that. So and in trying to fix this problem and recovering this dynamic correlation, we have implemented 2 different options or 2 different strategies. One is based in the multi-reference perturbation theory up to 2nd order, and the second one is related with the methods that try to incorporate DFT correlation into wave function methods. Let me start for the 2nd order correction to the RASCI wave function. So basically what we do is we define a 0 order Hamiltonian where we have the 0 order states and then excited states K, and that allows us to define an energy functional where we have the CI energy of the 0 order wave function, including Hall and particle contributions, and then a correction that looks like that look like a typical MP2, but that runs for all excitations beyond Hall and particle contributions, the ones that are not in the our truncation. Then in multi-reference perturbation theory, it's not there is not a unique definition for these excited state energies, and in Q Chem you can find two different options: this Davidson-Capui partitioning, which is based in the use of a Fokkian matrix, or the use of the Epstein-Nesbit energies. And then, like in other multi-reference perturbation theory methods, we have the option to use a level shift energy in order to, here in the denominator, in order to avoid singularities. This is something commonly done in methods like CASPT2. Okay, so basically what we have is like what we had before, but now we are introducing the effect of higher order excitations, in particular 1 hole, 1 particle, 2 holes, 2 particles, and so on, up to 2 holes and 2 particles with respect to RAS2 in a perturbative way. Okay, so and we have shown that this method works pretty well. And here, let me show you the case of the dissociation of N2, and we will use a higher spin reference, and as high as the one that I'm showing here. So this is septet, so 6 ampere electrons, and we use this configuration along the dissociation. So meaning if that we want to recover the ground state singlet along the dissociation, we have to apply an excitation operator that flips the spin of 3 electrons simultaneously. And if we do that for the RAS spin flip method, we obtain a smooth profile, but which is quite higher with respect to the energy that we might get with CCSD, for instance, or CCSD parenthesis D. Now, if we correct this with this second order perturbation theory, we now get basically very similar profile, smooth, but now at much lower energies and very close to this golden, CCSD parenthesis T, and in difference with these coupled cluster perturbation methods, we obtain, we have no problem at dissociation, right? And we have also tested this method for excited states. Here I'm showing a set of different type of pi, n pi, and sigma pi excitation in organic molecules. So these are singlet to singlet transitions. And here I'm showing you these 18 excitations of different molecules, and the error that we obtain for the vertical energy with RASCI with no perturbation theory. And you can see that the error can be as high as much beyond 1 eV, which is huge, while when we add this perturbation correction, we go in general below 0.4 eV, which is a large improvement. Okay, so this is the use of perturbation theory, and more recently we have been playing with the idea of mixing DFT correlation. So basically adding correlation energy for free to our RASCI wave function. And to do that, we use a range separation scheme where we split the Coulomb operator into a long range part that will be taken care of by our wave function, and a short range part that will be applied to or studied with DFT. And for doing this range separation, we use, as is common, the error function, and here we have the two contributions, the short and long range, and with doing that, we have now split the electron potential in terms of the long range and short range part. And with doing that, we can now have we can compute the energy of our states as a part that basically depends on the wave function, where here we have the the long range electron interaction, and then for the short range we have DFT, where we have the Hartree exchange and correlation functionals. And the separation between long and short range wave function and DFT is controlled by this range separation parameter, that when it goes to large values up to infinity, towards infinity, we recover the wave function, in our case the RASCI wave function, and if it goes to 0, we recover, or we should recover, a Q Chem DFT energy. And we have this method can be used for the ground state, but also for the excited states. And I won't go into the details, but we do that by defining an effective Hamiltonian and using a reference density, and this allows you to just with a standard diagonalization of our Hamiltonian to obtain not only the ground state but also excited states. And in Q Chem we have implemented this method with the use of different short range exchange and correlation functionals. Let me show you the performance of this method in the calculation of these the lowest lying singlet transitions in a sense, the LA and LB singlets. These are two states, as I said, the two lowest excited singlet states in these molecules. They have different symmetries and different electronic character, and they correspond to, in one case, basically the transition between HOMO-LUMO, and then LB, the combination of the transition from HOMO to LUMO +1 and HOMO -1 to LUMO. And here I'm showing you the errors that we obtain with pristine wave function theory and with the mixing of short range, in this case short range PBA, with different values of the range separation parameter. And we can see that, well, we have a very large error, or quite large error for RASCI, and this error is, in the case of this LA state, this error gets much lower when we include the short range DFT. But for the LB state, this improvement is not that clear. So basically, I would say that we, in general, get very similar errors. So we wanted to understand why is the case, and where are the limitations of this wave function short range DFT method, and why we get different type of results for different type of transitions, and we want to know if this is related with the systems with closed or open shell configurations, and maybe we want to try to improve this method. And for that, we went back to our toy model, the H2 molecule, and once again, here I'm showing you the dissociation with full CI and RAS spin flip wave function. So actually, for this case, with a RAS2 space of 2 electrons in 2 orbitals, of course, RAS spin flip is very, very close to full CI, and only at equilibrium we are missing some correlation, I would say dynamic correlation. So we thought, well, maybe this is the ideal case where, okay, we are very close to the exact solution. If we add here short range DFT, we should recover this small amount and get to full CI. So If we do that with using the same RASCI spin flip wave function, but now mixing in short range LDA, we obtain actually a much worse result. So we obtain a much lower energy at equilibrium and much larger energy at dissociation. So actually, this mixing actually produces a much worse result, and we wanted to understand why is that. So we computed the dissociation with our wave function plus short range DFT method, but now not only for the ground state singlet, but also for the triplet. But not only the ms equals 0 triplet, this one, but also the ms minus and plus 1 triplet. And we see that we obtain very different energies for the ms0 triplet than the ms plus minus 1 triplets. And we think, or we thought, that this must be related with the spin polarization effects in the DFT part. So we said, okay, so maybe we can, these effects are important here, and we might make a spin polarized version of this wave function short DFT method. Instead of using a spin alpha and a spin beta densities in the exchange correlation part, let's use these other type of densities that might include a spin polarization effects in multi-reference wave functions. And then we also look in more detail the different contributions to the energy of the short range DFT, and we split it along the dissociation for the different states, the contribution of the short range correlation here in red, and the short range exchange in blue. And you see that for the correlation part, there are basically almost no difference very different. So while we recover the same exchange for the triplet ms equals 0, we have a much lower or value for the exchange of for the T1 triplet. So clearly the exchange here, the difference emerges from the exchange part of the short range DFT. So we thought, okay, so let's replace the short range DFT for exact exchange, and when I say exact, I mean the Hartree-Fock short range exchange, and that maybe that would be an option to improve our results. And another option would be to, instead of using Hartree-Fock short range exchange, redefining the exchange from the wave function in this way. So basically is reinserting the short range into the wave function part, and then leaving DFT only to deal with correlation. So, and if we test now all these different options for, again, for the dissociation of H2, we obtain these results. So let me walk you through the different profiles. So once again, when we use our RASCI spin flip with short range LDA, we obtain now all the profiles are set to the 0 at the dissociation, and here we obtain a too low energy at equilibrium with respect to full CI. If we use the polarization approach, this one here, the spin polarization approach, we obtain now higher energy at equilibrium, but also we obtain a non-physical profile with this maximum that we know it shouldn't be there. So it doesn't work very well. And then if we replace the short range DFT exchange by Hartree-Fock, actually we get even worse results. And the only situation that actually improves things or gets closer to full CI is when we use this exact or wave function short range exchange, meaning that DFT only takes care of correlation. And now we are closer to the full CI and also to the wave function only solution. Now, this was for the ground state of H2. Now let me show you the computation of singlet triplet gap for these benzene molecules, the ortho, meta, and parabenzene. And here I will be testing the computation of this, the gap, the ground state singlet, and the first triplet with a wave function, which for us is the RASCI spin flip, the wave function with short range DFT, where in the short range we have exchange and correlation, and then the case where we only have correlation, short range DFT correlation. And for this last case, I will be solving this self-consistently, meaning that we converge both wave function and density here. And then I will use an approximation to this, which is we call a one-shot. So basically computing this part and then using the density to compute the correlation. So it's basically correlation energy for free. And if we do that, first of all, we can see that here in gray we have the values, the experimental values, and the singlet triplet gap goes down when we go from the ortho, meta, and para, which makes sense because the two radicals are more and more separated, so they interact weaker and weaker. And we can see that first, well, the initial wave function short range gives us very bad results, and the reason it was the same reasons as we saw for the H2 molecules. So the imbalance between a closed shell and open shell configurations, in this case between singlet and triplet, and then the RASCI spin flip wave function, as expected, already give us quite nice results, but we can see that if we add short range DFT correlation, for both options we actually get very close to experiment. And what we do is we get larger gaps with respect to the wave function because we add more correlation that is missing basically in the singlet. So we further stabilize the ground state singlet with respect to the wave function energies. So okay, so far I told you about the RASCI spin flip method, and I've been discussing this problem that we have with dynamic correlation and different, I would say, partial solutions to this problem. And now let me tell you about different computational tools that we have to characterize the states computed with RASCI spin flip or RASCI, and also to characterize electronic transitions between states. So we believe that characterization in detail of electronic wave functions is very important and help us to understand many different processes or properties of our molecules. And we are interested in knowing, well, how is the localization of our states, what is the distribution of charges in our system, do we have unpaired electrons, do we have local spins? So this is the kind of questions that we want to be able to answer for the wave functions that we compute. And for that, we basically use reduced density matrices, and this allows us to make a state-specific analysis. So we can analyze the ground state and also all computed excited states. And one thing that we can explore in great detail is this, what the unpaired electrons in the system, and for that we base our analysis in the one particle density matrix of any state, and in particular in the one electron eigen states of this density. The natural orbitals are their occupancies, and then we use some mapping to correlate the occupation number with an effective number of ampere electrons for each of these natural orbitals. So for that, we can use different type of mappings. These ones as were described by Martin Head-Gordon, and with these mappings, not only we can extract effective number of electrons in ampere electrons in our system, but also we can build, if we use the natural orbitals, we can build a density of ampere electrons, which give us a real space representation of the distribution of ampere electrons in our system. And of course, if we integrate this integral, we can have a metric for putting a number of the ampere electrons of our molecule. So let me show you two examples of the use of these tools. So here we have phenylenediol and triangulene. This one is a radical with a doublet ground state, and triangulene has a triplet state ground state with 2 electrons in these 2 degenerate orbitals, and we can compute the ground state of rather easily the ground state of these molecules with RASCI spin flip, and here I'm showing you the representation of the density of ampere electrons. So here where the ampere electrons are, in this case this would be basically this ampere electron, and we have a number that can be related to the number of ampere electrons, which is 1, or it's higher than 1, meaning that we have basically a doublet which has some additional correlation. And the same thing for triangulene, where now this is a triplet, and this would be the distribution of the ampere electrons basically at the edges of the molecule, like in the smaller case. And we can also give a number for the impaired electrons using this metric. And as I said, we can do that for the ground state, but we can also do that for any of the excited states that we might compute for these molecules. So this would be related with the number of ampere electrons, but we also have been doing a lot of work trying to characterize electronic transitions in the presence of more than one chromophore or chromophore fragment. And in this case, we are interested in decomposing our excited states in terms of local excitations, so excitations of a particular part of the system. For instance, in a dimer, excitations of one of the monomers, charge resonances, so excitations that move electrons between different parts of the system, and multi-excitons, or the simultaneous excitation of these different parts. And to do that, we can compute RASCI spin flip or RASCI in general states instead of using canonic orbitals, using fragment orbitals. So the first step is to localize orbitals in the fragments of our system. And of course, if we want to obtain or states with the same energy with or without localized orbitals, we must respect some rules. So in order to preserve the energy invariance, and then once we have these localized orbitals, we can apply our post-Rutherford treatment, and obtain the wave function and energy and properties, and then we make use of charge and spin cumulants and additional analysis tools, and finally this allows us to describe our electronic states, adiabatic states, I would say, in terms of these diabatic states that in the case of this dimer-like excitation would be contributions, local contributions, charge resonance, or multi-excitonic states. And let me go back once again to the H2 molecule to show you a very simple case where we can use this scheme. So now I will be computing the dissociation of H2, but using the decomposition of in this case, the ground state, not even an excited state, in terms of different valence bond-like contributions. So for the Hartree-Fock, we have one electron in the sigma alpha orbital and one electron in the sigma beta orbital. And if we express this as you can find in the textbooks, if we express this in terms of atomic orbitals, we have half of the wave function that has covalent-like nature, and half of the wave function which has a ionic character, and this is fixed in the Hartree-Fock wave function, and so we have left with this 50% of charge resonance character for this H2 molecule. Whereas in full CI we have not only this contribution, but many others that allows us to have a wave function which is flexible and can have any amount of charge resonance. Of what I mean by charge resonance by these configurations. So if we apply our tools to analyze now the full CI so wave function and the Hartree-Fock wave function, we obtain, as I said here, and so here we have the contributions, and in blue, in this blue solid line, we have the charge resonance contribution of Hartree-Fock, which as expected is 50%, so all along the dissociation, whereas the full CI we can obtain, we gather different amounts of charge resonance, much larger and closer to Hartree-Fock at shorter distances, and they obviously go to zero when we stretch the molecule. So we can recover this nice textbook example, if you wish. Okay, finally, let me tell you a little bit about a very recent implementation, which is the computation of a spin-orbit couplings between states computed with RASCI, which is of course interesting if, for instance, we want to do photophysics, and in particular if we want to study intersystem crossings. So like in other methods that are implemented in Q Chem, like TDDFT or equation of motion coupled cluster, we can compute spin-orbit couplings with RASCI in Q Chem using the Bragg-Pauli spin-orbit Hamiltonian, in which we have 1 electron terms and 2 electron terms, and typically this would require the computation of the one particle transition density matrix between the two states that we want to compute the coupling, and also the 2 electron density transition density matrix. But here what we do is we apply a mean field approach to this 2 electron contribution, and we as it has been done for the equation of motion coupled cluster methods in Q Chem, we made use of the Wigner-Eckert theorem, and where we have this density matrix and the Clebsch-Gordon coefficients, and these allow us to define a spinless triplet transition density matrix, where basically we have the difference between the alpha alpha and beta beta blocks of the density transition density matrix, and at the end of the day we can express the couplings within this mean field approach between 2 electronic states with spin S and M microstates with this expression where we have interaction terms, some coefficients that basically come from, they are Clebsch-Gordon coefficients, and this density matrix. And what is interesting here is that the dependence on the M values is only in the Clebsch-Gordon coefficient. So here there is no such dependence in this matrix, meaning that we only need to compute, for instance, the singlet and the MS0 triplet, and from there, using this expression, we automatically can gather the couplings between not only the MS0 states, but also for MS1 or MS -1, and in general between any two MS values without the need to explicitly compute them. So here, let me just show you a simple example. So this is this butadiene molecule, and these are the frontier orbitals, the LUMO, which is a pi star, and then we have two n orbitals as OMO and OMO -1, and this pi orbital. And if we compute the excited states, we obtain this distribution of singlets and triplets, and the spin orbit couplings that we compute, as expected, they follow the LCIET rule. So we have non-zero values between states which are pi and n pi stars states. Whereas if we have the same character, the couplings go to 0. And what is interesting is that RASCI recovers or gets couplings very close to EOMCCSD, which could be seen here as a reference method for this state, which are basically single electron excitations. And we have also implemented ideas already used for EOMCCSD, but now for RASCI wave functions in order to characterize the spin orbit coupling. So basically, what we do is a single value decomposition of this U matrix in order to understand the nature of the coupling and the magnitude, but looking at the Hall and particle contributions to this spinless density matrix. Okay, and with that, I want to finish. So the conclusions basically are, once again, the outline of the talk, and I hope I help you to better understand the RAS spin flip, our RASCI in general methods, and why we have a problem with dynamic correlation and some possible solutions to it. And I hope I have also convinced you that in Q Chem we have very powerful tools to characterize the states computed with this methodology. And with that, I want to thank the people working with me, and in particular Aaron Rodriguez, who has been an amazing work developing the methods that mix the RAS spin flip wave function and short range DFT, and Abel Carreras, who has been doing many different implementations in Q Chem, for instance, the spin orbit coupling, but many others. And outside of my group, also for sure and related to this work, Anna Krylov and Pavel Pohilko and Paul Zimmerman, and in Q Chem, Jinjian Feng and Evgeny Evgenikov, and of course to all of you for your attention.
Thank you, David, for this informative talk. And we have a couple questions so far, and feel free to submit your question through the question box. So our first question, the performance of the RAS short-range LDA looks good, looks great. Is there any reason not to use the short-range portion of PBE, PW, or other correlation functionals to handle benzene or TM molecules?
Okay, so if I understand correctly, the question is related with the use of the different functional short range functionals with the wave function, right? So
Mhm.
so from our experience, we don't see large differences between different type of short range of functionals. Short range functionals. So basically, in many cases here, in the different examples, I've been showing you results either with one functional or another. But when we test different functionals, short range functionals, we obtain very similar results. Either if we use short range LDA or short range TGA functions, and it makes sense, right? Because we are basically not including we are only including short range, the short range part, and there I would expect that LDA should perform quite well already, and that's why we don't see much difference between these different type of functions.
Thank you. A second question. So in general, for the RASCI calculation, what's the memory bottleneck?
Yeah, so the memory bottleneck. So this is the size of our wave function, right? And basically the bottleneck is the RAS2 space, like in CAS-SCF. So the size. So the method is the idea is to trying to have a method that does not need to go to very large RAS2 space, but this is the bottleneck. So the computationally this is the bottleneck, the size of the RAS2 space, which means the memory that we need to allocate for these CI vectors.
Mm-hmm. Thanks. Okay. Looks like we don't have more questions. Okay. I'm going to move to close the webinar. And if you're looking at the this video through YouTube, you can submit your question to our forum post about this webinar, or you can email me out. And I would like to thank David for this interesting talk. And I also want to thank all the attendees for listening.